Hello everyone, I hope you are doing well. So in today's video, we are pretty much going to go through the 2022 Physics Exam Part 2 of the short answer questions, where we'll be continuing off from questions 11 to 17. And so like always guys, before I start this video, if you guys want private tutor in specialist methods, physics or chemistry, you can always email me through this email. Let's smash through this video. Let's do this. Alright, question 11. Explain why muons formed in the outer atmosphere can reach the surface of the Earth even though their half-lives indicate that they should decay well before reaching Earth's surface. Alright, there's two actual explanations of this. I'm going to explain them both. So you basically have what we call the surface of the Earth here, and you basically have a elementary particle, the muon. And we know that it goes down towards the Earth at relativistic speed, so basically speeds close to the speed of light. And so, remember, if it's going at relativistic speeds, there's relativity. There's now, relativity is very common. It's going to happen here. So, basically, this is what happens. Now, by theory, because of the, let's estimate, let's say, joke around, so 10 microseconds. This is the half-life. Basically, what it means is, when it basically decays, the time it takes to decay. So, basically, the half-life is so small that it should decay around here. It should never actually reach the surface of the Earth. That's what the theory is by classical physics. That's what they basically predicted. And, when they basically looked at the surface of the Earth, they realized what? That there was actually muons. And they're like, how? How could muons reach the Earth, given that they're, basically their half-time is very small. And so basically when they realized that relativity is very significant here, they realized, So there's two ways that basically you can basically explain the question. You can answer this question. So the first one is by length contraction. So what happens is this. So you basically have the muon, and in the muon's frame of reference, it's actually gonna go through length contraction. So what does that mean? Well, what it means is basically, you know how the floor is basically here? This is the distance, the actual distance, this is where the floor is basically. And so realistically, it should never reach it. But because of length contraction, what happens is in the muon's frame of reference, the floor is going to be around here. So it's actually contracted. That length is basically contracted. So then the muon actually reaches the Earth. So in the muon's frame of reference, it sees that the length is actually smaller. So basically then it collides with the surface. So that's one reason. So we can explain that because of length contraction in the muon's frame of reference, it's, the surface is much closer to it, so it does reach it. Now, the second part is actually by time dilation. So basically, let's say you had a scientist here, or the Earth's, like basically he's looking at the Earth's perspective, or frame of reference. So what happens is basically the scientist is gonna witness time dilation. So this here is our proper time that is basically measured by the muon. So basically, the muon realizes, oh my god, my half time is 10 microseconds, and I can't reach that surface of the floor. But for the scientist, he's going to experience time dilation. What that means is basically time will be basically longer. So basically, he realizes that for his time here, it takes basically 15 microseconds. So so now the half-life is basically longer. So meaning that it won't decay here, but it will decay here because it has more time before it decays, and hence it does reach the surface. And so that's also another way you can basically explain it. And yeah, these are the two ways basically when you're dealing with muons in any exam setting questions. It's all about length contraction in the muon's perspective and time dilation in the Earth's perspective, or the scientist's frame of reference basically. And yeah, that's what we just got to explain. I'm just basically going to explain only one of them because it's only 2 marks. Basically, just the, the time dilation. What we just explained using time dilation. Beautiful. All right, so let's say muons are traveling at relativistic speeds due to time dilation. So dilation, they reach Earth. So basically, they reach the Earth's surface before decaying. The half-life in the Earth's frame of reference is greater than the half-life, measured in the muons frame of reference. Beautiful. I mean, that's only 2 marks. Yeah, I think that should be enough to get those 2 marks. And yeah, beautiful. Question 2. Let's have a try at this. Students conducted an experiment in a physics laboratory using a laser light source, 2 narrow slits, and a screen as shown in figure 10. Alright, so it looks all good. Point Z is at the center of the pattern of the light and dark bands on the screen. The slit separation is 0.1 millimeters and the distance between the 2 slits is at a distance of 2 meters. The band at C is a bright band. Explain why at point C is bright and why there's a dark band to the left of the center. What a beautiful, easy question. So to get basically full marks for this is what you need. So you need to basically explain the path difference for each. So at point C, and of course it's a bright, that means that there's constructive interference. So you basically, all you're going to need to say is, for example, for point C, where it's basically because the path difference is 0 at the center, hence constructive interference occurs. That's all you have to say for C. And also D will do the same. So you just need to say the path difference and the what happens. So constructive interference. Constructive interference occurs, basically giving a bright band. Beautiful. That's it. Now 4 point, basically the one that's left, you can see that the number, sorry, but basically it is black, but because of I'm using a black and white template, this is actually black, this part here. So this here is basically going to be at n equals 1, basically. It's the first, basically node to the left. So basically your path difference, we know that your path difference, so we know that path difference, because it's destructively interferes, is n minus half lambda, which is basically, if you sub in 1, it basically gives you 0.5 lambda. So that's our path difference at the dark band. So path difference is 0.5 lambda. So that's basically giving you what the path difference is. And then we just explain that destructive interference happens. Destructive interference occurs, giving dark band. Beautiful. And that's it. That should give you those 2 marks. Nice. So whenever you get questions, explain why this is a, point C is basically like a bright band. You just basically talk about the path difference and then state if it's constructively or destructively interfering. Beautiful. B, let's have a look at this. The experiment performed by the student is often described as Young double-slit experiment. Yes, explain how the experiment gave support to those who argue that light has a wave-like nature. So this is very easy. It comes up in many exams, this question. I've seen it in like every exam. It has like, how does Young double-slit experiment, basically that experiment, support that wave model, basically. Well, how does it do? So basically, it's very easy. All you need to say is basically, because there are dark bands and light, like the bright bands, this is due to constructive and destructive interference. True. And so interference is basically a wave property. We know that. So hence this supports the wave model. That's all you need to say. These are, because it's only 2 marks. Yeah, it's the most easiest 2 marks. So you just need to say basically the dark and the bright bands is basically due to constructive and destructive interference, and hence interference is a wave property. So fast experiment supports the wave model. Beautiful. These are the only thing that you basically need to write. So you can say the light, so the bright actually, the bright and dark bands formed are due to constructive and destructive interference. Beautiful. Interference is a wave property. or phenomenon, you can say. Property. So interference is a wave property. Fuss experiment supports the wave model. The wave model of light, basically. Nice. Next question. The frequency of the laser is this. Calculate the spacing in the dark bands on the screen show you're working out. So basically we want to calculate change in X. So change in X is basically what? It's your wavelength over L over D, basically. And so how do we calculate our wavelength? Well, we have our frequency, and we know that our wavelength is basically your speed of light over your frequency. So basically, let's calculate that. So 3.0 times 10 to the power of 8. Your frequency is 6.8 times 10 to the power of 14. Hence, you get a basically wavelength of, okay, so 3.0 times 10 to the power of 8, 6 times 10 to the power of 14. That gives me such a small number, but it's basically, alright, so it's basically 5.0 times 10 to the power of, so 1, 2, 3, 4, 5, 6, 7. -7 meters. That's your wavelength. Basically sub that in to this formula. So your wavelength, you need to sub in a wavelength. 5.0 times 10 to the power of -7. Your length between the, it's 2 meters. And the sleep separation distance is 0.10, so 0.1 millimeter basically. So 0.1 times 10 to the -3, that's going to change it to meters. Does that look right? Yep, 0.1 times 10 to the -3. Beautiful. So putting that all on my calculator, sorry, I get basically 0.01 meter. Beautiful. Yeah, done. So the students decide to safely immerse the entire apparatus in a liquid. The refractive index of the liquid is unknown, but it is greater than the refractive index of air. Using the same laser light, they notice that the spacing of the band changes. Describe the change observed in the spacing of the bands and explain why this has occurred. Okay, let's think about it. Okay, so what we've done is basically we went from, a low refractive index to a high refractive index due to the fact that we went from air to basically some water or some liquid. So we went from basically a, low refractive index to a high refractive index. And so basically what happens is that the speed of light actually decreases. It becomes slower when it goes from low to high. So your velocity or your speed decreases. And so if your speed basically decreases, let's think about it. We know that what's going to happen to those bands is we just need to find out change in X is lambda L over D. So L and D are constant, but it's this here that's going to change your lambda, because we know that, velocity, so your wavelength basically is velocity over frequency. Now, frequency is basically the same, of course, it's constant, but your velocity, because it had decreased, we said, your wavelength it also has to decrease. So if your wavelength decreases here, it means that your change in X or your spacing is also going to basically decrease, and that's it. So for 2 marks, we're just going to basically write it much nicer like that. So basically, your overall it's going to decrease. Your space of those bands are going to decrease. So what you're going to say is basically the dot point what you said. So like refractive index increases. Basically overall, so it increases. The speed of light decreases. So we also know that the wavelength then also decreases. And hence spacing spacing of bands will also decrease, Beautiful, and that's it. 2 marks. Question 13, let's have a try at this. A ray of green light from a light-emitting diode strikes the surface of a tank of water at an angle of 40 degrees to the surface of the water. as shown in figure 11. The ray arrives at the base of the tank at point X. The depth of the water in the tank is 80 centimeters. The refractive index of green light in the water is 1.335. Calculate distance OX. Outline your reasoning, show you're working out, give your answer in centimeters. All right, so basically OX is this distance here. All right. Well, we know, okay, we just need to basically, how can we calculate? Well, we know the distance this, which is 80 centimeters. That's very useful because we know that the distance is 80 centimeters. We just basically need to calculate this angle. And that's easy because this angle is your refractive angle. That's your refractive angle. And so, remember, this is your angle of incidence here. I think a lot of students will make that mistake. It's not this one. Remember, it's always to the normal, basically. The angle from the normal to the ray. So basically, so to get the angle, it's basically 90 minus 40, which is basically 50. So that angle is basically 50. All right, so it's 50 degrees. So let's try to calculate your angle, your refracted angle. So we know that N1 sine theta, your incidence angle must equal to N2 sine your refractive angle. So N1 is basically coming from the air, and your sine is 50. It would be N2, which we're going to 1.335 sine theta r, sine theta, which basically what is happening is basically then it'll become sine inverse. So to get your theta r is basically going to be, so sine inverse of sine 50 over 1.335. All right, that looks perfect. So yep, done that. Yep, that looks perfect. So let's put that in a calculator. And so that gives me basically a 35 as my angle of, basically this angle here is therefore 35. So your refractive angle is 35 degrees. So basically this angle is 35 degrees. Now let's think about it. So we know it's a right angle triangle. So we know that this is your hypotenuse. So you know this part here is your hypotenuse, this is your opposite, and this is your adjacent. Now we know adjacent is 80 centimeters, and we want to find OX, which is our opposite. So TOA, so we're going to use tan. So basically tan theta, which is tan 35 actually, is opposite, which is our OX, divided by the adjacent, which is 80 centimeters. So OX, the distance, is basically 80 tan 35 degrees, which gives me 80 tan the angle. I get basically 56 centimeters. Beautiful. Not too bad. B, the green light is replaced with a narrow beam of white sunlight. Describe the color of light that arrives to the left of point X, at the point X, and to the right of point X. So, all right, let's have a look at this. So if you're changing it to basically a white sunlight, you're basically now, it's going to have dispersion. Dispersion is going to occur. And so basically light will split into its, because, in that full spectrum of light, your visible spectrum, every light basically has different wavelengths. And so it's going to split due to the wavelength. So we know that basically for dispersion, we know this. Let's rub this out. All right. So at the left of X, what's going to happen? So we know this. We know that because we're going to basically, we know that the lowest, having a low wavelength, bends more, has a more, it bends more to the normal. So having a lower wavelength bends more to the normal. So the ones that have the lowest from the whole visible spectrum, the lowest wavelength means the highest frequency, which is basically violet or purple. So basically, the one that's going to come here, around here, that's close to the normal, as you can see, bend more towards the normal, will be purple. Beautiful. Light at point X. So light at point X is going to be basically green. Still, it's going to be green. So it's not going to change. It's still going to be green. So light at point I is the one that actually doesn't bend the most to the normal, which is basically the red, because that has basically the greatest wavelength of light, which is red. And that is it. I mean, this is, you don't need to know this because this is not anymore in the study design. Like, refractives, dispersion, all these stuff are gone out of the study design. So these are great, but yeah. All right, question, let's see that, yep, so question 14. Let's have a try at this. Sam undertakes a photoelectrical effect experiment using the apparatus shown. She uses a green light filter. Sam produces a graph of photocurrent in milliamps versus voltage as shown, figure 13. So identify what point P represents on the graph in figure 13. That's your stopping voltage. Easy. So your stopping voltage. Sam then significantly increases the intensity of light. If you increase the intensity, remember what happens is your photocurrent increases. Sketch the resulting graph on figure 14. The dashed line in figure 14 represents the original data. So remember, basically what just happens is if you increase your intensity, you increase your photocurrent, basically. So it's going to basically have a higher photocurrent, but still come to the same stopping voltage, like that. Beautiful. Then Sam replaces the green filter with a violet filter. Remember, if you're going from green to violet, violet is much more, it has a higher frequency. So you're basically increasing your frequency. Keeping the light source at an increased intensity. So you're basically still increasing your intensity. And now you've increased your frequency, which basically increases your stoppers. It will increase your stopping voltage. Sketch the resulting graph on figure 15. The dashed line in figure 15 represents the original data. So we know that the stopping voltage will increase, so it'll be here. And also, of course, our current has been also increased. So it's basically going to look like this. Basically a straight line. That's it. Nice. Further experiments produce figure 16, a graph of the maximum kinetic energy of emitted photoelectrons versus frequency of light. All right. Nice. Determine the work function in electron volts of the metal surface used in the experiment. The data is produced in figure 16. Okay. So basically, you remember the work function is basically where the y-intercept is. So we can see that the y-intercept is basically 3.4. So it's going to basically, it's negative 3.4, but remember its energy, you make it positive. So 3.4 electrovolts. It's only 1 mark, so you just need the answer. E. From the graph shown in figure 16, calculate in joule seconds the value of the Planck's constant show you're working out. Easy. Remember, the Planck's constant is the gradient of this line. So, but we want it in joules per second. So what that basically, no, joules seconds. So because this is electrovolts per frequency, what we just need to do is we're going to calculate the gradient, but make sure to convert this to joules, not electrovolts. So that will guarantee us correct. So I'm going to pick these two answers here because these are the most easiest. Of course, they've given us that. So that point is what? So it's basically 0, negative 3.4. And this here is 8.10. 8.1 times 10 to the power 14. Don't forget about that. So what we're going to do is, so your h, your Planck's constant, is basically your, so it's going to be 0, so basically your gradient, so it's going to be 0 minus 3.4, which is 3.4. So basically 3.4. Then basically your frequency is 8.1 minus 0, which is basically 8.1. But make sure you times 10 to the power of 14. So this will give me an electrovolts per second. Remember, we want in joules, so we basically, this is our energy in electrovolts. We want to make sure just basically make it into joules. So I'm going to bring it here. I'm going to multiply by 1.6 times 10 to the negative 90 to make it back to joules. So here should give you my Planck's constant. 3.4 times 1.6 times 10 to the power of negative 19. 8.1 times 10 to the power of 14. Beautiful. And so that gives me 6.7 times 10 to the power of negative 34. Beautiful. State one limitation of the wave model and explain the results of the photoelectrical effect. Now, there's a lot, but the most significant one is the negligible time delay. So let's think about it. So what the wave model basically predicts is that because, so what it basically believes is that energy can actually be delivered over time. For example, if you have a photoelectron here, you can hit it with any frequency, because what it believes is that energy will accumulate over time until, the electron basically releases due to going above the work function. It's like this. So imagine your work functions here. So basically, what happens is you just leave basically the light open, or you leave the light on it. Basically, it's going to just accumulate basically energy until it goes beyond the work function, and it'll be released. So there should be like a time delay they should measure. like a time delay. That's what the wave model predicts. But when they did it in the photoelectrical effect experiment, what they found out that there was no time delay. So that's one thing that it basically couldn't explain that was right. And so yeah, so we can say so basically no time delay. I mean, this will get you the answer, but I just want to basically so delay. All right, so no time delay as the wave model. So what's happening here? So wave model predicts energy is delivered over time. So there should be basically a time delay. But yeah, there is no time delay. You cannot explain it. That's the limitation of it. Easy. Beautiful. Next question, 15. Figure 17 shows some of the energy levels of an excited neon atom. These energy levels are not drawn to scale. Okay. Show that the energy transition required for an emitted photon of wavelength 640 newtons meters is this. Okay, so we know that energy of the photons is basically h2 over wavelength, where basically your h value is your Planck's constant, but we want to write it in electrovolts. So basically it's going to be, where's my summation? 4.14. So 4.14 times 10 to the negative 15, yep, times your speed of light, divided by the wavelength, which is 640 times 10 to the negative 9. Make sure it's in meters. That gives me 12.14 times 10 to the negative 15, 3.0 times 10 to the power of 8, 640 times 10 to the negative 9. And so that gives me 1.94 electrovolts. And yes, we have proved it basically. All right, that's easy. 1 mark. On figure 17, draw an arrow to show the transition that would emit this photon. All right, let's see. So 19.8 minus 13. Nope, that's too large. What about this one? 20.0. What about this one? So 20.02 minus 19.8. That gives me 0.22. No, it's very small, so that's not true. Maybe this one over here. Photon basically releasing from here to here. So 20.65 minus 19.8. Still 0.85. We're getting closer, so basically it needs to be a little bit much larger. What about this part here? 21.74 minus 19.8. 1.94. Yes, it is. So basically, it's going from here to here. So let's draw a nice transition. So it's basically going to go from here down to here. It's going to transition. So basically, it's going to emit 1.94 electrovolts of photon energy. Done. Question 16. A small sodium lamp emitting light of wavelength 589 nanometers is viewed at night through 2 windows from across a street. The glass of one window has a fine steel mesh covering it and the other window is open, as shown in figure 18. Assuming that the sodium lamp is a point source, at a distance, a physics student is surprised to see a pattern formed by the light passing through the steel mesh, but not pattern for the light passing through the open window. She takes a photograph of the observed pattern to show her teacher, and who assures her that this is a diffraction pattern. Beautiful. State the condition that the fine steel mesh must satisfy for a diffraction pattern. Of course, okay. So diffraction, for the condition for diffraction, we know that diffraction is proportional to your wavelength over width. Now, because they're both given the same wavelength, because the lamp is basically using the same sodium lamp, the only difference is their widths basically. And so you can see that the width of this one here, because they're basically small little width of each of those rectangles are basically, or squares, are basically so small. So if your width is small, your diffraction becomes significant. This here, overall, has a very big width. And so it's basically, what that means is, because it has a very big width, it means your diffraction becomes less because you're increasing your denominator. So the question just state the condition that the fine steel mesh must satisfy for a diffraction pattern to form. Okay, like we said, so for a diffraction pattern to form, we know that your diffraction ratio, your wavelength over width, must be greater or equal to 1. This is the condition to have significant diffraction. And so what that basically means is that, yeah, you basically, I think, would say this, and you just need to say that, okay, the width of So the width of the meshes, these little holes, the width. So remember, we want to make sure have this ratio, make sure it's the same. So basically that means the width must be less or equal to your wavelength, basically. So yep, does that make sense? So if your width is less, yep, or equal, so it can be equal, yep, that's going to be greater or equal to 1. If your width is very small, yep, it's always going to be greater or equal to 1. So that's our condition, basically. We want our width to be basically less or equal to our wavelength. And so that's what's actually happened here. Because if you can see that there's diffraction pattern happening in this mesh, it just means that the width is actually less than the wavelength of light, that 589 nanometers. All right, that's what we just basically, I think, have to say. So for a diffraction pattern to occur, the width of the mesh steel must be less or equal to the wavelength, basically. All right, as from this ratio must be greater or equal to 1 to have significant diffraction, basically. Beautiful. Explain why the condition stated in part A does not apply to the open window. Of course, the open window has a big width. It means that if you have a big width, it's a very large width, you won't have diffraction because it's basically less than 1. Your ratio is basically less than 1 because your edges of the frame that have such a large width, it's bigger than the wavelength. It's very, very large. So hence, diffraction is not observable because the ratio is less than 1. Yeah, for 2 marks, I think you just need to say that. Okay, so the distance between the edges of the window frame, it's very large. Basically meaning your width is large, so compared to the wavelength, meaning that the ratio must be less than 1. Your wavelength of width must be less than 1. Hence, diffraction is not observable. Diffraction is not observable. Beautiful. This is not a too bad question. How many? 3 marks. Yeah, nice. Question 17. I think this is the last one. Yep. Let's have a try this. So, a material scientist is studying the diffraction of electrons through a thin metal foil. She uses electrons with an energy of 10 kiloelectrovolts. The resultant diffraction pattern is shown. Calculate the de Broglie wavelength of the electron in nanometers. Beautiful. Let's do that. So it's 4 marks. So basically what I'm going to do is make the energy. This is your kinetic energy, basically. And I want to make it into joules. So basically, it's 10 times 10 to the power of 3 electrovolts. That's kiloelectrovolts. But what I'm going to do is I want to multiply it by 1.6 times 10 to the negative 19 to get it basically in terms of joules. So 10 times 10 to the power of 3 times 1.6 times 10 to the negative 19. That gives me 1.6 times 10 to the power of negative 15 joules. And so we know that momentum is equal to basically 2 times your mass of the electrons times your kinetic energy. Which basically means 2 times the mass of an electron times your kinetic energy will give me 2 times that, 9.1 times 10 to the negative 31. So yep. Times that gives me basically 5.39 times 10 to the power of negative 23 kilograms per meter second. That's my momentum. So I've got that. Now, all I have to basically say is that your, we know that wavelength is h over your momentum, sorry. So what's our wavelength? Your de Broglie wavelength, we want it in nanometers. So basically it's going to be 6.63 times 10 to the negative 44. I'm putting that on here. Times 10 to the power of negative 23. Beautiful. So that gives me So 6.63 times 10 to the negative 34 divided by the answer. That gives me overall 1.2. It's so basically 1.22 times 10 to the power of negative 11. But of course, it's in nanometers. So I'm going to basically times the 10 to the power of 9. And so basically it gives me 0.012 nanometers. That's easy. Beautiful. B. The material scientist then increases the energy of the electrons by a small amount and hence the speed by a small amount. True. Explain what effect this would have on the de Broglie wavelength of electrons and justify your answer. Easy. So if you're basically increasing the speed by, you've increased the energy of the electrons, so your speed basically increases, your velocity increases. And so what basically that means is that your kinetic energy increases. So if your kinetic energy increases, remember P equals the square root of 2mke, it means your momentum has also increased. Now, wavelength is, remember, h over your momentum. So if your momentum has increased, your wavelength decreases because your denominator is increasing. So overall, the wavelength will basically decrease. And that is basically it. So overall, the wavelength decreases. So let's explain that. So an increase in speed, will increase momentum, since an increase in speed will increase momentum. So since wavelength is basically proportional to 1 over so what am I saying? Since an increase in speed will increase the momentum, we know basically, increase the momentum. We know that frequency, your wavelength is basically proportional to 1 over, so it's proportional 1 over to p. So meaning that an increase in speed will increase momentum, since wavelength is proportional to 1 over your momentum. An increase in momentum will lead to a decrease in wavelength. Decrease of wavelength. And that is it. I think it's very easy for 3 marks. For a question, so it's a nice, easy marks. So yes, an increase in speed will increase momentum, since yes, your wavelength is proportional to 1 over p. True. We can actually write it like this also. So we know that momentum, because it's equal to h over p, which is momentum, we can write momentum as mv, meaning that wavelength is basically proportional to 1 over v, basically. So if your velocity increases, your momentum, your wavelength decreases. So that's perfect. And that is it. Nice. I hope you guys enjoyed this video and learned something from this video. Please make sure to like and subscribe for more future videos. I hope this video finds you well, and please make sure you take care of yourselves. Bye bye.